Yeah, Grizz, a lot of people did. All right, now it's on there forever. I love this. Moving on. I don't want to be here. I want to be here. All right, this has three different answers. One, delta y, dy, and then this is the error. Right, it's the error estimation. Let me say, without interruption, that this does not give you y values. It gives you changes in y values. Okay? So if you're going to estimate something, you estimate things, and then there's an actual change. You subtract it, and that's the difference. So this is an estimation. This is the actual change. This is an estimation. This is how far apart they are. Is your estimation really good? Is it really off? Okay? So, I don't really want to crank out these equations again. I'll do it one time just for fun. Yeah, I'm going to use x equals 1, delta x equals 0.02. Okay? Okay, delta y. Okay? Delta y we can do on the calculator, right? I can do it on the calculator? Yeah, I can take the function value of 1.02 minus the function value of 1. That's what it is, isn't it? This is a fancy way of saying f of 1 plus 0.02 minus f of 1. Right? Which is the same thing as saying f of x plus delta x minus f of x. Get the idea? Okay. So you go to your handy dandy calculator. Booyah. Clear. I think I'll just take the lazy way out. X cubed. No, I'm not going to do that. I'll go to the home screen. 1.02 cubed caret 3 minus 1.02, sorry, 1.00 cubed. Enter. Now, this doesn't give me the y value. It tells me the y value between the two values went up 0.061208. Okay? That is not the y value. That is the change in y. So y increased a little bit as x went from 0.02, or as x went from 1 to 1.02. Okay? It went up. So, if I want to find the value of, I'll leave it right there. If I want to find the value of delta y, I take the derivative, which is 3x squared, which in this case is 1, and I multiply it by 0.02. So what's 3 times 0.02? 0.06. So you can see using the differential to approximate the change is close to the actual value. How close is it? Well, that's what this is saying. Take it and subtract it. What is delta y minus dy? Right, 0.061208 minus 0.06, and you get 0.001208. In other words, it's pretty accurate. Okay? I did not use any symbols through that because I'm more after the applications today. I did a lot of symbol stuff yesterday. You can do the equations. There's a few problems for homework you can do. But I wanted to find the values. I want to see how the numbers worked. Okay? Questions on that? Fantastic. All right. I think it's time to move on. I don't see anything else down there. I see a pull tab. I don't want to pull it. All right. Ooh, this looks exciting. I have no idea what this is doing here. Oh, I know what this is. It is. This is the same picture we had yesterday. Notice the pink? If the increment for x is very small, then the function value can be approximated using the linear approximation. This is where you get to the point of approximating like the square root of, say, 31. I'd say the square root of 35. That's my favorite question, the square root of 35. Okay? I like that question. I like it a lot. I know. All right. Now, actually, I didn't know that. But anyway. Now, I'm going to be asked the question of Matthew Hamer. Why? Because I can and I want to. Ready? Then let's say this is my square root function, square root of x. Okay? Great. And I want to know, what is the square root of 35 going to be equal to? I've never explained it like this before, so it's kind of interesting. I'm doing it like this. I have no idea what's going to happen, but I'm excited. Yeah, you are. The square root of 35 is going to equal some decimal, correct? So that means 35 is going to be down here as my, value I want. Okay? What's wrong? There's stomach pains back there? What? Nice! All right. So you approximate the square root of 35. What square root do you know is close to 35 that you know the answer of? 36. Okay? So if I want, I could use the square root of 36 to give me my initial point or my initial value, correct? Okay? Oh, it's not working. Yikes. Oh, yeah, I'm in trouble. All right. Square root of 35. Square root of 36. So I can use that as my initial value, correct? If I drew the slope of the tangent line, and I used the differential of y, that gives me the approximate change between these two values, doesn't it? dy f prime of x dx gives me the change in y, doesn't it? Okay. I'm fighting it here. Give me a break. It wants to go south on me. I'm not going to let it. F prime of x equals, come on, stop. There we go. Equals the change in y. Okay? So, I can tell you how far it changes. How is that going to tell me what the square root of 35 approximately equals? If I know the change between these 2 points. Well, I just picked 6. It is a square root of 36. So if I have my initial y value, I can add the change in y to get my new y value, can't I? That would work, wouldn't it? My initial y value plus the change in y gives me my new y value. Well, you add it. Okay? So if I take a look, let's say f of x equal the square root of x. Okay? The derivative is going to equal 1/2 x to negative 1/2, isn't it? Okay? So, my initial y value is the square root of 36, and that's 6. I add to that 1/2 of 6, 36, to the negative 1/2 times negative 1. Why is delta x negative 1? Why is dx negative 1? I bet 36 is my initial starting point. What's my next one I'm going to use? 35, it's down 1. Okay? So, what is the square root of 36? It's 6. You already calculated, right? So that's 1/2 times 1/6 times negative 1. Because my dx is the change in x. I went from 36 to 35.
And how did you get the 1/2 and negative 1/2?
That's the derivative of my function.
Oh,
So what is 6 minus 1/12? Well, it's obviously 5 and 11/12, isn't it? Isn't it? Great! 5 plus 11/12. What's the square root of 35? That's pretty close. So if somebody asks you to approximate the square root of 35, you could say 5 and 11/12. And that would give you 2 or 3 degrees of accuracy on your decimals, right? That's pretty accurate for a quick calculation, isn't it? So that's using what's called the linear approximation. Why is it called linear approximation? Because you're using a line to come up with the values, okay? We're going to study 3 or 4 different types of approximating, all to give you a higher degree of accuracy quickly, okay? Linear approximation gives you a great degree of accuracy as long as your numbers are close. If you pick numbers far away, you lose the accuracy. For instance, I did not pick on my square root function. If I want to approximate the square root of 35, I don't think I'd be close if I used 4. Would I? I'd be quite a ways off. So in linear approximations, you have to be close. So you're going to have to use values that you know close to what you're trying to find. That's how mathematics works. You use what you know to try to find something new, then you use that to find something else. Okay? How we did that? Well, easy. We wanted to approximate the function value, let's say, of x sub 2. We said that approximately equals the function value of x sub 1 plus the derivative of x sub 1 times dx. X sub 1 was my nice number. What did we change from yesterday to today? Today we're putting a y value with our change to come up with a new y value from a function we're trying to approximate. Okay? That's we know this is the change in y. Change in y. And we know this is our original y value. Original y value. Is it written in the book like this? I don't think so. But it's close. I mean, it means the same thing. Wait a minute. Yeah?
Why did you put x up there if x is
You could. I can change that to 0, 0, and change that to a 1. That's how subscripts work. Right. Usually the lower subscript is your initial value and the higher ones are further down the line. Oh, unless you're talking about stats. P66 is different than P17. We learned that today. And P90X is different than all of them. All right. Wait a minute. Taylor knows the answer to this question. This is known as a linear approximation, correct? Right? Take a look at what this looks like. Are you ready? B plus mx. M is the slope of the tangent line, x is your change in x, and b is your y value. That's where it comes from. That's why it's called linear approximation. It comes from the slope-intercept form of the line. Yes? Yep. F prime of your initial value. Okay? Back. There we go. Nice. See, there's no record of it except for this audio recording. Ready to move on? Let's move on. We're not out of time yet. I'm feeling too good to be out of time. Oh, Trig! Grizz, you're so losing focus this year. If I do a brain break, there's no way you get through the homework. All right, Kylie, are you ready? Kylie Stewart's going to help me on this one, so everybody else be quiet. Even the sine of 61 degrees. Ready? Well, is loosely approximated by, oh, I got a little carried away there. The sine of 61 is approximately equal to the sine of 60 plus, Kai, what's the derivative of sine? Cosine, positive. And then 60, and how much is this changing by? Look, even my daughter knows you go from 60 to 61, you add 1. It was in her second grade workbook. The problem is it's 1 degree. And in calculus, we don't like degrees. We like radians.
Can we just show no calculator?
Times the conversion from degrees to radians is what, Elizabeth? Yeah? Very good. 180.
Wait, so
You have to have a real number here. You cannot have a unit. Okay?
why is 1 degree there?
Because you're changing from 60 to 61. This you're changing theta. If you want to get technical, you can say d theta.
So it's always a 1 degree multiplied by pi over theta, or is everything multiplied?
This is one product. Okay? So what's the sine of 60, Kylie? Very good. Square root of 3 over 2 plus cosine of 60, 1/2 times pi over 180. And that gives me square root of 3 over 2 plus pi over 360. And that is your final answer. No degree symbol right there or there. That's it. That's how they wrote almost all of the trig exact values. You have decimals, they have those. You look up in an old math book, you'll see these values for a lot of sines and cosines, and you wonder what the heck they came from the differentials of calculus. Now, to check that, how much accuracy do you think it's going to be?
0.0012.
Is it? Oh, okay.
3 decimal places.
Second square root of 3. I'm getting some people aren't very excited about this. Plus second pi divided by 360 sine of 61 mode degrees. Ha ha. How close is that? Well, minus, well, I could subtract them, I don't want to. It's pretty close. I mean, if you round to the 4th decimal place, you're right there. No, you're not. 3rd decimal place. Okay, so that's nearest thousandths. It's pretty good for no harder than the equation is. But remember, use nice numbers because this is before, way before graphing calculators. Use nice numbers because you're trying to find something quickly that gives you some degree of accuracy. Okay? Using differentials to approximate the change in y instead of the actual change in y. Differential is an approximate change. Okay? An approximation to a rate. Those two sides means it's time to go on. I got one from this side of the room and that side of the room. That means we're moving on. Find a limit. We just did that. Wait a minute. Yeah, we did. Interesting. Oh, spherical balloon. Sweet. You ready? Ooh. I did.
How would you see
Number
a
30.
cubicle?
This is number.
No, it is cubic. 30. No, it's either. It's just not in there. They're like different.
Quiet, please.
Dad,
Thank you very much.
Can you back to your old ways?
Sure.
Go back to like.
Look, I colored the slides to try to please one person.
No, I just mean it's not. It will not please all of us if you go back to your old ways.
Oh, what number is this?
It's not in the book.
Nice. All right.
Based off something.
Yeah, they're kind of like made up.
Can you?
The radius of a spherical balloon is 12 inches. Wait a minute. This has maximum air. Quiet, please. Plus or minus 0.06. Approximate the maximum air in the calculated volume of the sphere. Ready? Close. Chase, in your textbook, there's a definition for maximum air and relative air, I believe. Oh, keep going. Go further back. What's the average air? Delta W over W is the average error. Okay? So this one, the radius. Yep, it's like dy over y, dr over r, dv over v, dx over x. Thanks. The radius is 12 inches. Quiet. Now Chase. Any idea what to do next?
Well, you take the maximum can be.
What's the question asking us to do?
Maximum error.
Of volume. So I have to find dV over V. What is dV equal to? No? dV is equal to what? No, I think it's V prime of R dr over the volume. No, now take a look at something. When I had dy, we said it equal to f prime of x dx. Why do we use x instead of t? No, x was in the equation, wasn't it? What's in the equation for volume if you're talking about a spherical balloon? The radius. What is the equation for a volume of a sphere? Chase, what's the equation for volume of a sphere? 4/3 pi r cubed. What's the derivative of v with respect to r if you have 4/3 pi r cubed? How do you take the derivative of that? You take 4, take the 3 out in front and multiply it. So you have 4 pi r squared. And then this dr has to be in there because that's your equation, dr. Nice. I'm almost ready for some numbers, I think. Well, you see that 4 and that 4/3? What's 4 divided by 4/3? 3. So dV over V, because it said what's the maximum error of the volume. It said in our notes or in the book that the error was the change of something over the original. Kind of like dy over y. So I have dV over V equals 3 4/3, or 4 divided by 4/3. Pi divided by pi is just 1. What is r squared divided by r cubed? 1 over r, and then I have dr over r. Now you got a decision to make. Are you going to use the number 12 for r, or are you going to use the plus or minus 0.06 for dr over r? It says the radius has a maximum error of plus or minus 0.06. What do you think that represents? Yeah, the differential of r. In other words, you could be 6/100ths high or 6/100ths low. You could be at 12.06 or 11.94, somewhere in between there. Either way, that's what this number is. 3 times plus or minus 0.06. Where does the 12 go? In this case, it doesn't go anywhere. It's just part of the problem to get this set up. So, that's pretty easy. Plus or minus 0.18. I need some units, I think. Inches. Oh, volume is in what usually characteristic? Cubic inches. Inches cubed. How do we do, Chase? Did we get the right answer? Not even close?
I assume we got the right answer. Just wait. No, it's not.
I don't know if we did or not.
It's an example. It's not
Oh, it is in the book.
That's not a real problem in a book. You didn't use the same numbers, so.
it's approximately.
Plus or minus 0.01.
Yeah, plus or no, minus 0.5%. They divided by 12, they didn't use the 12.
Well, I didn't use a 12.
But they took the 3, they didn't have
Oh, the DR is plus or minus. I get it. Sorry.
100 or
And they divided it by 12.
That's right. Thanks, E. Save the day. Phew. 3 plus or minus 0.06 all over 12. Nice. Right. So we have to take our change divided by the original amount. Phew, that was close. That's almost enough for today, I think.
Yeah.
How much time we have left?
6 minutes, not enough.
I haven't got the 5-minute warning yet.
Can't we just take
5 minutes.
3 and
Now, does that work out?
No, it would just be.
5 minutes.
0.01 plus or minus 0.015.
0.015? Nice.
And do we have to take that by 100?
Oh, I didn't want percent. I didn't want percent.
Yeah,